We introduced a new formulation for barycentric coordinates that allows us to represent multiple kinds of coordinates, some of the ones that existed previously, but also new deformation-aware ones.
Welcome to Talking Papers, the podcast where we talk about papers and let the papers do the talking. We host early career academics and PhD students to share their cutting-edge research in computer vision, machine learning, and everything in between. I'm your host, Itzik Ben Shabbat, a researcher by day and podcaster by night. Let's get started. Hello and welcome to Talking Papers, the podcast where we talk about papers and let the papers do the talking. Today we will be talking about the paper Variational Barycentric Coordinates. This paper was published in SIGGRAPH Asia 2023 journal track, and I'm happy to host the first author of the paper, Ana Dodik. Hello and welcome to the podcast. Can you introduce yourself?
Hi, great to be on. My name is Ana. I'm a second year now PhD student at MIT. I'm co-advised by Vincent Sitzman and Justin Solomon, and my research lies sort of at the intersection of geometry processing and machine learning.
And who are the co-authors of the paper?
Yeah, so the co-authors, I've already mentioned my co-advisors, Professor Sitzman and Professor Solomon, and also Professor Oded who used to be a postdoc and is now faculty in LA at USC.
Great lineup of authors. So in a TLDR kind of format, 2-3 sentences, what is this paper about?
Yeah, so I guess there are two ways of looking at it. At a lower level, it's a new way of doing cage-based deformation that allows sort of for more control of the final look of the deformation. But if you zoom out a little bit, we're really introducing ideas that are similar to a lot of the stuff you see in, for example, physics-informed neural networks to the world of geometry processing, which is the part that I personally find really exciting about this work. So it's sort of a different way of solving some of the problems that we're used to solving in geometry processing.
All right, this sounds super interesting, but I think we need to kind of take a step back and start defining stuff so people can understand what we're talking about, right? So this would go into the intro section of the paper, I guess. So when you're talking about cage deformations, what is that?
Yeah, so cage-based deformation, I'll maybe start off with the input-output behavior of the algorithm. So as the input, you're given a shape that could be like, a 2D drawing or a 3D mesh that you want to animate, you want to deform it somehow. And you're also given a cage. So this could be like a polygon in 2D that surrounds your little drawing, or it could be, another lower resolution mesh in 3D. And so the wanted behavior is that if you deform the cage, so let's say you move a vertex of your polygon or you move a vertex of your mesh polytope, it should propagate that deformation, the cage deformation, into the interior and onto the shape that you want to deform. And so what our algorithm is tasked with doing is computing what's called the barycentric coordinates. You can think of these as sort of the interpolation weights that specify, if you deform a vertex to a new position, the weights of that vertex define the region of influence, or sort of how what part of the interior should move together with that vertex.
Right. So just to kind of, I don't know, explain this maybe in different words. I like to imagine this. Let's say I have like a mesh which represents an object, right? So armadillo is really kind of a cool example that you guys used in the paper as well. But it's kind of like, imagine you have like this marionette, a doll in the real world, but you can't move the specific fingers or arms, but you can move like a whole cage around them. And then the question is, well, if you deform it, the cage, if you deform like the thing that wraps everything in one way, what happens to everything that's inside? What happens to the mesh, right? How is it deforming?
Yeah, that's precisely it. Yeah.
Right. So, but why is this an important problem to solve? Why do you need to do these deformations? What is it good for?
Yeah, that's a great question. So there's multiple paradigms for doing character deformations out there. Cage-based deformations is one of them. The typical thing you might think of is having a skeleton and using that to deform. Cages tend to sort of give you slightly more control because they're so, you can represent different kinds of deformations with them that sort of might not be possible with skeletons. So it's part of the standard artist's toolbox. And I think one of the things that was interesting to me here was that it was an area where I could see a clear benefit of rethinking the problem in a way that would give artists more control. So a lot of the previous methods tend to sort of give one set of weights that they say are the best, and what we really wanted to do is sort of allow the artist to look at the final deformation and maybe choose a different set of weights to best fit their needs.
Yeah, this brings me to the question. So what are the main challenges here in this kind of problem?
Yeah, so there's multiple challenges. I think the technical challenges, we can get more into them when we get into the method section, but barycentric coordinates specifically are like a very finicky thing to work with because they are defined in terms of constraints. So if you think of the coordinates of a vertex as like the region of influence that vertex has, these constraints should be that like a control vertex cannot have negative influence over a region, or it has to have 100% influence over itself, and there is a really tricky one to deal with in our setting, which was the property that an undeformed cage has to reproduce the undeformed shape on the interior. So I think on the technical level, getting that to play nicely with this idea of having multiple possible weights for the artist to choose meant that we sort of wanted to use neural fields because they're sort of very amenable to changing the objective function, but then how do you actually build all of these constraints into the neural field? And so that was the main technical meat of the paper. And then there's also like the higher level questions of how do you what types of deformation weights are actually useful for artists.
Yeah, I think this is one of the reasons I really like this paper, because like you're taking this something like all of these constraints for barycentric coordinates, like this existed for a while now, right? Decades, I would say. And you're kind of fusing this new neural fields, I would say, world into that. You're kind of injecting that insight to use that powerful tool, but then you still have to kind of meet the requirements, right? You have to satisfy these conditions, and that's not always easy, right? Some of them come trivially, some of them like automatically are satisfied, but some of them you kind of have to do some work and tricks and smart stuff that you did in the paper that we're going to talk about in a bit. But before we do, let's talk a little bit about related work, right? So before reading your paper, which one or two papers should people read?
Yeah. So I think previous work falls into two categories. There's sort of the set of closed form solutions, which tend to be really fast to evaluate, but often will violate some of these constraints, these barycentric coordinate constraints, and they really lack flexibility. So they give you one set of coordinates, and that's what you have to use. There is so these would be, for example, Wachspress coordinates or mean value coordinates are the most famous one. So that would be a really good starting point for this field in general. And then there's the constraint optimization whole approach to it, which basically formulates this as, discretizes the interior, sets this up as a quadratic program, solves it. So by definition, it will like satisfy all the constraints, and it's optimization based. But it does require you to like mesh the interior, which is sometimes not as easy if you just download a random mesh off the internet. And often has limited flexibility because they sort of present you with one smoothness energy, and that's what you have to use. So that would be, for example, harmonic coordinates, or local barycentric coordinates, which I think is sort of the closest paper to ours.
Okay, super interesting. I'll make sure to put links to these specific papers in the episode's description. All right, let's get down to it. So let's talk about the approach. What did you do and how did you do it?
Yeah, so we really wanted to set out to have a new way of optimizing for barycentric coordinates that was flexible to the objective, so we could do deformation-aware coordinates. We really wanted to keep it mesh-free because we didn't want to wait for tet wilds or have tet gen crash on us all the time. And we really wanted it to satisfy all of these constraints by construction, which would then allow us to sort of just swap objectives in and out. And to do that, we started off with sort of a fairly simple neural field. So there is no learning happening here. We're just using a neural network as a representation. The neural network takes as input. So the first thing you might do is have a neural network that takes as input, a point in ambient space with X, Y, Z coordinates, and gives you as many numbers as there are vertices. And then you could think of sort of, well, maybe we can use softmax to make them all positive and sum up to 1, which are 2 of the constraints. And maybe there is some way of enforcing another one. But this reproduction property, that like the thing that comes out of your network, if your cage is at rest pose, should reproduce the interior. That was a really tricky thing to do in that framework. So what we had to do is come up with a new mathematical formulation for the problem. And in doing that, not only did we come up with this sort of neural field approach that had this flexibility, but we also learned something new about barycentric coordinates in general, which is sort of very exciting to use this like very new hammer and then find something fundamental out from it. So I can go a bit more in detail on the exact formulation. Yeah, so what we ended up doing is decomposing the shape. So let's say you have a polygon as your cage, and so we're operating in 2D. Think of you're animating a little thing that you drew in Illustrator, and you have a polygon that you're using as your deformation cage. What we ended up doing is taking all the vertices of the polygon and connecting all triplets of vertices into what we dub virtual triangles. So this is a large set of them, gross cubically if you're following along, that it's an overlapping set of virtual triangles. The reason this is useful is that triangles satisfy barycentric constraints by construction. So there is no degrees of freedom in the optimization problem. And so the barycentric coordinates for simplices, triangles, and tetrahedra are very simple to deal with. So once you have that, the barycentric coordinates of the polygon for every point on the interior can be expressed as a convex combination of these virtual triangle barycentric coordinates. It's sort of hard to wrap your head around, possibly over voice,
maybe I'll recap, right? So you got your polygon, and you just take all the vertices and you create a bunch of triangles from every possible 3 vertices that exist in this polygon. But let me ask you this. So why use these, and you call these virtual triangles, right? But why use virtual triangles? Why not mesh the polygon in some, like do a triangle mesh in some way?
Yeah, that's a great question. Multiple reasons. I think when you're in 2D, meshing the interior is perfectly fine because triangulations are a lot easier than tetrahedralizations. That ends up taking you into this realm of what previous work did, of setting up a constraint optimization problem and solving that.
And you guys want to be independent, right? You don't want to be dependent on the triangulation.
Yeah, so I think you really want to, in some scenarios, you really want to avoid having to do triangulation. Again, in 2D, it's not that big of a problem, but if you just download a cage mesh off the internet, it is highly likely that it will be non-manifold and ugly in all kinds of ways and have overlapping triangles and will break most of your tetrahedralization software. And so also these, cubic solvers tend to be either slow or limited in sort of the amount of detail you can represent. So this is sort of an alternative approach. The reason why we do virtual triangles and instead of sort of any arbitrary set of triangles is that, as we show later in the paper, this is like a very fundamental decomposition of your shape for this problem. And we end up proving that this specific decomposition can represent every possible set of barycentric coordinates. So it's sort of a universal barycentric coordinate function approximator, if you will. And we also end up proving that for a randomly initialized network, whatever comes out of that network are also valid barycentric coordinates.
Yeah. So the main reason why I asked about the meshing thing is because, well, these virtual triangles, you get a lot of triangles, and that's hard to process. But then you have like a step where you kind of prune them, right?
Yeah. So there's two parts to this paper. First part is the theoretical construction that we come up with, and I should mention that a similar construction comes up in an old mesh parametrization paper from 97 by Floater. There are some stark differences, but it is very similar. That being said, once you have that mathematical formulation and you've proven all of these nice things, there's the part that's actually making this run at a reasonable pace and do something useful. And so for that part, we had to deal with the practical nature of the fact that these virtual triangles grow cubically and quartically in 3D if you're dealing with virtual tetrahedra. So we come up with a pruning strategy to deal with that. The pruning strategy is based on saying that we want our virtual triangles to be local to the vertex, which, it follows the ethos of previous work, saying that these coordinates should in general be local. So I don't
when
think
you
we
say
actually
local,
lose
you
that
mean
much.
that if a triangle is kind of stretches to far away, then you're going to toss it, right? You're not going to use it as part of your virtual set.
Exactly. Yeah. You don't want, if you're animating a character, a vertex close to the fingers to be moving the toes.
Yeah, makes sense. Okay, so now you have your virtual triangles. What's the next step?
Yeah. So for a point on the interior, the polygon barycentric coordinates can be expressed as a convex combination of all the virtual triangle barycentric coordinates for all the virtual triangles that surround it. So that is the construction we're dealing with, and now we have a neural field that takes in a point on the interior and predicts a weight per virtual triangle. We zero out all of the virtual triangles that don't surround a point on the interior. And then we basically use the convex combination ways that we got from our neural network to combine the virtual triangle barycentric coordinates into the polygon barycentric coordinates.
The input to your network, to your radiance field, is a coordinate in the polygon, and the output is basically the weights per virtual triangle, right? Where it's a fixed number because it's all the virtual triangles, but you basically zero out all the triangles where this coordinate is not a part of. It's not inside, right?
Yeah, that's precisely right. Yeah.
All right. So is that it?
Yeah, basically that is sort of your architecture, and then the fun part is choosing what you want your weights to be. You have this construction. There is one thing that there's sort of one detail in there that you have to take into account, is that if you want to optimize smoothness energies in the style of physics informed neural networks, our construction is discontinuous, so we come up with a suitable modifier to do that, to smooth out these discontinuities. And now you can basically optimize your favorite, Dirichlet energy, total variation, things like that. And this is the bit that's like really exciting to me, because it's sort of quite different from the way we typically do these sorts of problems in geometry processing. So unlike previously, where maybe you discretize the interior, set up this quadratic problem as a PD, and then set up the constraints in CVX, maybe even hand derive a version of whatever your favorite optimization algorithm is for it. This is really, we sort of created an architecture that bakes in all of the constraints. So you really don't have to deal with that. Everything is end-to-end differentiable. So you can, you really don't have to worry about what energy you're using. Neural networks tend to be in practice deal well with non-convex objectives and stuff like that. And then you're basically doing computing the integral of your energy over your domain by doing Monte Carlo integration. You're throwing random samples and sticking them into SGD, and comparing that to defining your finite elements. It's like a different way of doing things, and I think it comes with a lot of benefits.
Yeah, and I think this is like the best bridge possible to start talking about the results. So yeah, what did you use it for? Like, which applications, which experiments did you do?
So we show results on a lot of the standard things that have been done. So your favorite total variation, weighted total variation, Dirichlet energy. But then where things get really interesting is that we looked at this sort of weighted total variation example, and the weights are very localized, hence the name of the previous work, local barycentric coordinates. And this works in some cases. In other cases, it will create sort of bending effects where that might not be desirable. So if you think about deforming a human elbow versus deforming a cat tail, if you use a cage and the same set of coordinates, they will produce sort of different results, and that might not be desirable. So we said, well, what if an artist could make a deformation and then look at it and say, well, actually, I want to make this more rigid, or something like that. So we show an example like that, where you can take the last frame of an animation, compute an energy of that deformation, and minimize that to get a deformation that looks different. So you would basically back propagate all the way to the coordinates to make the animation more rigid, or things like that. So that is one of the applications. Another one was sort of more of a toy example, which was inverse deformation. Let's say you do a physics simulation, and you now want to maybe compress it using a deformation cage. So you want whatever's on the inside of the cage to act in accordance to how it would if it was dropped physically onto the floor. If you solve, you can set up an inverse problem. You take your a simulation output and you optimize. You start off with some set of barycentric coordinates and a cage in rest pose, and you optimize just the position of your cage. So you backpropagate all the way to the vertices of the cage. And if you just optimize that, you end up with sort of noticeable artifacts, and it doesn't represent the simulation result very well. If you also backpropagate into the weights, we achieve a much better result. Now, I have to say this is not like that specific example is not production ready yet, because it is only one set of coordinates. So, but I can imagine a future where you have weights where maybe they are meant for like deformation weights. If you're compressing a rubbery simulation or something like that. So that is something I find very exciting as sort of like an avenue for future work.
Yeah, keep something for the conclusion and future work section. So basically, just to sum up what you're saying, right? So the fact that you have this energy term that you can just choose whichever term you want gives you a lot of freedom and a lot of flexibility in what the output is going to look like, right?
Yeah, exactly. So usually if you read these papers, they will say our coordinates look smoother or more local or things like that as arguments for why their coordinates are better. We really try to say, well, why don't we let the artists look at the final look of the deformation and then choose optimize the coordinates based on the artistic intent.
Really interesting. Yeah, giving this level of flexibility to artists, designers, people that work with these kind of animators, I guess, people that work with software that generates this kind of that uses these kind of tools. And this is super interesting and relevant. Were there any fail cases?
Yeah. So I think there's a number of, I'll call it avenues for future work. One of them is that our pruning heuristic sometimes fails. So the pruning heuristic is based on extrinsic distance. So if you have like a shape with a lot of concavities, it will sometimes lead to triangles getting rejected that shouldn't, and possible visible artifacts. In 3D, there is a lot of discontinuities that get created through these virtual tetrahedra, and a lot of virtual tetrahedra as well. So just waiting for the optimization is somewhat on the slower side, and I wouldn't necessarily call it a failure case, but there are situations where the discontinuities remain visible in sort of, I think you can see it in one of the meshes in the paper, in the results.
Right.
It's not something we ran into commonly, but it has happened, yeah.
Yeah, and this is something interesting for future work, right? Finding a way to prune the virtual triangles or tetrahedra in such a way that avoids this entirely, right?
Yeah.
Cool. Were there any unexpected results or findings?
I think what was unexpected is that we sort of came up with this formulation because out of desperation, because we didn't know how to constrain a neural field to do these things, and then ended up proving that it's sort of a fundamental decomposition of this problem, like of this function class. And I think the proof of that is really like sort of clean and neat and insightful. And what ends up happening is that if you have this high dimensional constrained polytope that has all of these planes that constrain your space, these virtual triangles are actually the corners, or like the basic feasible solutions of a linear program, if you like that language. So it means that sort of any solution for barycentric coordinates is like a convex combination of these virtual triangles. And we only realized that sort of like halfway into the project. It's not something that we came up with. So I thought that was sort of very fun.
All right, conclusions and future work. How do you see the impact of the paper going forward?
Yeah, so what I really hope is that people pay attention to this sort of more physics-inspired neural network way of solving geometry problems, because I personally just find that so exciting, that you can now add all of this flexibility through this approach. When it comes to future work, you hit the nail on the head. I think a better pruning heuristic would be something that's might be necessary for if somebody wanted to productize this. Another thing that I think is possibly doable is adding smoothness in as a constraint, so then you don't have to add this mollification, the smoothing of the discontinuities, and they would be also the coordinates would be smoothed by construction. I haven't figured out a way to do both that and keep all of these, proofs about the fact that like we represent the whole function space and so on. But I have some leads. So I think that is sort of on the like immediate term. On the more long term, I am personally very excited about ideas of well, what if we remove the really hard constraint and just optimize for skinning weights, which is like a related problem. Can we get that to work really fast? Like we've seen a lot of these very fast nerfs, or Gaussian splatting is all the rage now, I hear. So to just sort of get this to work at interactive rates, to give artists really real-time feedback on this. Another avenue that I find really exciting is making these pipelines more data-driven. So there was no learning in this project. We just use this as a representation. I really think one of the main benefits of neural networks is the fact that they can be combined not only as a representation, but also learn from data. And we have a lot of videos of things moving. So that seems like a good prior if somebody was to work on this. And lastly, I'm personally also very interested in the human aspect of all of this and how artists interact with these tools, and if what we're doing as researchers is actually useful to them, or are we just running in circles by ourselves? So I am personally also very interested in seeing what tools we can design around things that are coming out of these new ways of optimizing for all of these problems.
Yeah, I think like so first, to address the first part that you said about the nerf kind of and Gaussian splatting kind of hype now. I think like back when nerf just came out, then the field kind of split into two directions, right? One was about getting the results to be more accurate, and the other one was how do we make it super fast, right? And here it's a similar question, right? How do we make it super fast so it's, as you said, works at interactive level, so designer have feedback, but also like get, well, I don't know if better accuracy, but like the whole pruning part that we were talking about, how do we kind of improve on that? And yeah, I think like the last thing you said is super important. Like, are the tools that we're researching, because it's super interesting for us, is it useful in the real world where people actually use these tools? And I don't know, to me, I'm a researcher. To me, it sounds like this is something that could be really useful. But yeah, it would be interesting to get that feedback and kind of, see in a year's time where this landed.
Yeah, I completely agree. I think it's so important to have multiple levels. I will get bogged down in fun math for a very long time if left to my own devices. But I think it's so important to actually zoom out and look at the whole forest and see what it is that I'm actually building. So,
yeah, super important. But I mean, it depends on the person, right? Like, there are a lot of researchers out there that don't care about the usefulness. They just want to do fun research, fun math. But to me, as an engineer in training, then to me, this is like, yeah, things need to work in real life as well.
For sure, yeah. I also, I like building things, so I think that's where I'm coming from with this.
Cool. All right. And now to my favorite part of the podcast. What did reviewer 2 say? Please share some insightful comments you had in the review process.
Yeah, great question. Besides the standard, we want 700 more experiments type SIGGRAPH feedback, I found the reviews to actually be very insightful and useful, and have peer review works sometimes. So a lot of smaller things like improving the exposition, but I think some of the reviewers got also a bit excited about the paper and asked us to think about questions that maybe we haven't thought of. So somebody asked, could you formulate energies to reproduce existing like mean value coordinates and things like that, which might be useful because previous like handcrafted coordinates sometimes violate constraints. So if you could get something as close to them without violating the constraints, that might also be a useful thing. I've gotten the question of like, does this work in higher dimensions quite a number of times, including in the review process. So like theoretically, yes, this should work with hypersimplices. You just have to deal with the quintic growth factor then, which, might be possible, but I personally haven't tried it. And yeah, I think in general, I think the peer review like greatly improved the quality of the final paper.
Yeah, and I have to kind of give a shout out to the SIGGRAPH review process. I think it's so coming from more of a vision world. Like I publish mostly in vision venues, and a lot of the process is sometimes random, and you don't always get like experts in the field. And I think SIGGRAPH, you get a lot of very valuable feedback because actual experts in the field are reading the paper and doing the review, and this is a great way to actually kind of like you said, that peer review works. It's about the peers, right? Who is doing the review?
Yeah. I do want to share one sentence. It just occurred to me from a reviewer that I found very satisfying to read as an author. We got somebody, I presume this is sort of like a person that has a lot of classical geometry processing background. And they said that they're generally highly skeptical and pessimistic regarding machine learning based papers. However, they love this article. So I found that so validating to I love breaking people's misconceptions about things. So, yeah.
Yeah. And I think this is it's the next step, right? It's just, there are very powerful tools in different worlds of research. And it's always very powerful to merge them together into new works and new ideas and new research. And this is how cool things happen. And
yeah, this is such a great point. I think the computational landscape today looks so different, both hardware and software, from the way it did 15, 20 years ago when the first papers on this came out. So yeah, I think it's a really good time to be doing a PhD right now.
It's always good to do a PhD.
Yeah.
But yeah, I have to agree that now is an amazing time, especially because we're seeing kind of what the tech world, the tech industry is looking like, and the salaries but to me, it's all about following what you're passionate about.
For sure, yeah.
Well, yeah, it's always good to know that the review process works and still making things better. Okay, so it's time to wrap up. Ana, thank you very much for being a part of the podcast. And until next time, let your papers do the talking.
Yeah, thanks for having me on.
Thank you for listening. That's it for this episode of Talking Papers. Please subscribe to the podcast feed on your favorite podcast app. All links are available in this episode description and on the Talking Papers website. If you would like to be a guest on the podcast, sponsor it, or just share your thoughts with us, feel free to email talking.papers.podcast@gmail.com. Be sure to tune in every week for the latest episodes. And until then, let your papers do the talking.